So thank you very much for these kind words and for the invitation to give this lecture. So my chair is actually also multi-hazard risk dynamics, and I would like to explain in this lecture, say what kind of work we're doing under this chair within within our group here at the faculty ITC. We'll look at what multi-hazard risk is, what are the different aspects of it, and what makes it dynamic. But let's first start with a simple introduction as to the concepts that we're looking at. So as we all know, risk is a function of hazards, vulnerability, assets, and capacity. It's often being dealt with as an individual level, whereas multi-hazards are multiple major events, the hazards that an area face within a specific context. And these events might have particular interactions, spatially, temporal, and related to their occurrence, as we will see later, and which makes that prediction very much more complicated. We will see that a lot of work actually has been done here more on the forensic analysis rather than on the predictive part of it. So when we want to look at disaster risk, we are looking at probability of losses. And so we would like to do this in a forward mode, but also considering the fact that most of these components will have a very large dynamic. So we would look at climate change components that have a feedback on the multi-hazards, but also land use, population change that would also be driven by climate change, but would have an impact on the characteristics of the assets within a particular area. So we would then be considering a multi-hazard risk assessment that it would consider the possible and relevant hazards and that we compare them, but also to see what is their joint say function in terms of causing impacts. And this impact could not be just only direct, but also indirect. And so this is actually still a rather complicated field, which is still under development. There have been also quite a lot of research projects that aim to develop methodologies and frameworks to better address this particular problem. So my framework put it here on the right side. That's where we're looking at probability of losses. That has a number of individual components. The multi-hazard component, where we are looking at hazard interactions, the spatial and the temporal relationship, the frequency of those events. We would be considering the assets with their characteristics, how they interact in terms of exposure, and how we would deal with vulnerability, either in a physical context, as vulnerability curves or matrices, or in a more holistic way as indicator values, and then how this links to risk reduction in terms of using risk information for risk-informed planning. Before I do that, let me first explain you a little bit about my organization, and I do this on the basis of a small presentation that I want to share with you about my organization. I hope you can hear.
In 1950, ITC was founded by the first Prime Minister of the Netherlands, Willem Schermerhorn. Originally named International Training Center for Aerial Survey, ITC's focus was on aerial photography and mapmaking, intending to establish base maps for countries without a spatial infrastructure. But the world has changed since our founding over 70 years ago. ITC has grown into an internationally recognized, leading faculty that, with the use of spatial data, contributes to global development and resilience. We still love maps, and not only those on paper. However, we don't just make them. We also collect data for those maps by combining satellite data and pictures from drones. We analyze and visualize this data, and based on these insights, we help policymakers take informed decisions, answering questions like,
how can mobile mapping reduce risks and disasters?
How can we monitor droughts and predict crop yield?
And where and when do diseases occur?
In our line of work, we look at these issues and the threats they pose to humankind. To stop these threats, all United Nations member states adopted the Sustainable Development Goals, and we are passionate contributors when it comes to solving these goals with our research, education, and capacity development. From all over the world, people come to the Netherlands for our multicultural community. But we also share our knowledge as guest speakers at events or online in our digital courses for working professionals. And our graduates become part of the worldwide ITC community of over 25,000 alumni. This way we solve global challenges with local actions. For more than 70 years and with many more years to come, we keep educating people here at ITC. Faculty of Geo-information Science and Earth Observation of the University of Twente.
Okay. So as you can see, we are not a normal faculty, but we have been founded in order to do capacity building of people from majority world. And our, I would say, biggest asset are the 25,000 alumni that have returned mostly back to their countries, have become heads of departments, even up to ministers, and that form a global network with whom we collaborate up to this day. We provide training, still postgraduate training at different levels, in different courses, humanitarian engineering, spatial engineering, and geoinformation science and Earth observation. We have basically 4 major focus areas within our faculty on resource security, that deals with biodiversity, but water security, but also rare earth minerals, deal with geospatial AI, so AI being very important component within all the different fields, but here we look specifically at geospatial AI developments. We have an important field focus area on urban futures, as more than 50% of the world is now living in urban areas. We also expect that to increase a lot over the coming period. And we have a focus on disaster resilience. So within that focus on disaster resilience, we have a center for disaster resilience where we collaborate with different organizations within the Netherlands, Europe, and globally. And we provide also our, say, research and outreach within that center. We focus there on 3 major components, say the hazard and exposure assessments, monitoring and early warning, multi-hazard risk assessments, say for the long future, but also real time using impact forecasting, and also say tools for disaster response and recovery planning. So we do this type of work, say, globally. We work with master students that come from many different countries, or PhD students, and we do international projects. We support national governments, for example, in the development of national scale multi-hazard risk assessment methods. Upper left here, an example of work we did for the World Bank in the Caribbean, where we supported 5 countries in setting up their geo-databases and using it for disaster risk management. Or we work, for example, on early warning systems, like the bottom right example for Indonesia. Here, one example of such type of applications for Central Asia, here at the country of Tajikistan, where we developed a risk platform via UNDP for the national government, which gives information on a number of different hazard types, exposure asset types, and generates per administrative unit a risk profile for each of those combinations of hazards, which can also be downloaded and be, used at different levels of administration. Currently, we are involved in a large European project in which Funda and myself are the coordinators. This is a Horizon Europe project called Paratus, and the aim of this project is to develop an open and user-centered platform for systemic risk assessment. So we're looking at complex interactions of hazardous events, and we develop tools that stakeholders can use to assess those, to analyze them initially, but also to quantify certain parts of it, to use them in serious games, and also look how they change in future. It is a project with 19 partners, with a duration of 4 years. And let me give you a small intro of this project through a video.
Earthquakes, droughts, floods, and extreme events are a growing threat to the lives of millions of people around the world. As disasters become more frequent, their effects may happen closer in time or trigger related hazards. These are called compounded disasters. The Paratus project aims to improve the preparedness of practitioners, scientists, first and second responders, decision and policy makers, and citizens in case of disasters. To gain a deeper understanding of the hazard interactions, Paratus began by learning from historical disasters through the use of impact chains, a tool that helps reconstruct and visualize a disaster event and its impacts at a glance. Building on those insights, the Paratus project is developing new methodologies to assess risks across sectors and geographical settings. These methods will be used to analyze changes in risk over time and space, and to develop new scenarios and mitigation options with stakeholders, using innovative tools like serious games and social simulations. The results of the Paratus project will be available in an online platform where stakeholders can get information about the risks in their area and simulate the effects of compounded disasters. These services are being developed by a unique transdisciplinary consortium of research organizations, NGOs, SMEs, first and second responders, and local and regional authorities. They will be tested in 4 application studies in the Caribbean, the Alps, Bucharest, and Istanbul. The Caribbean is one of the most disaster-prone regions in the world and is expected to worsen due to climate change. On the border between Austria and Italy, we aim to provide stakeholders with tools to manage potential transportation disruptions. Paratus will support national organizations in emergency intervention in Bucharest, one of Europe's most endangered capitals to earthquakes. As a megacity with over 10 million residents, Istanbul experiences unique challenges, including earthquakes and floods, alongside rapid population growth and urban expansion. Do you want to increase Europe's resilience to compounded disasters, counteract economy-wide damages, and be better prepared? Join us at the Disaster Risk Stakeholder Hub and contribute to the online platform.
So as mentioned, one of the key outcomes of this project is to co-develop with a number of other European projects a disaster risk stakeholder hub that brings together information and tools to help decision makers to better mitigate the effects of compounding disaster events. There have been quite a lot of different projects over the years that look at multi-hazard risk, but one of the disadvantages is that after the end of the project, most of the materials get lost, they are no longer visible. And what we wanted to do is to bring together all these different tools in a sustainable way with partners that also would keep those alive over a longer period of time. So we've been developing the stakeholder hub in the course of this project, and when the project ends, a next project would take that over. And we formed together like a cluster of projects with about 20 different projects that all are committed to collaborate here. Maybe this also is a nice link, perhaps also to the 8th IDRiM initiative, whereas we also organize webinars regularly, where we present the results of these projects. Maybe a quick look at this stakeholder hub before we continue. The stakeholder hub is a tool which has an information section and a simulation section, so where users can get information, for example, on information on disaster databases, but also important here is our impact chain wiki. So impact chains are a very important component of our project, where we co-develop together with stakeholders like a mind map that would show what kind of impacts have occurred in the past with historical events. And then in the next phase, actually look at what could be the impacts of future events, how impacts would cascade from one sector to the next, and where interventions would be most suitable. So these are, there are tools that we use for this. One is called Kumu, and we also brought together a series of impact chains that we've developed for the different case study areas. For example, here, an example for the Caribbean. Let's just look at one example, how it is seen, for example, in the online tool. So the impact chain itself could be a fairly complicated sequence of events where we differentiate between hazard events, impacts, vulnerability, exposure, and also adaptation options, and where each of those is hyperlinked to information on that particular component. And we are currently also developing the linkage between these impact chains and spatial information, where we link it to a shareable data platform called the Geo-node. So through this, we are, developing these impact chains and then seeing how we can quantify certain components of that, and how stakeholders can use those impact chains to better reduce the impact of disaster events. We also have a number of other options within our within the stakeholder hub, for example, about sharing data on exposure, vulnerability, loss and damage, loss and risk reduction, and best practices. And we have a simulation component, so where stakeholders can actually use open available tools to do a hazard assessment or a risk assessment, or use for serious gains. The platform is also intended to collaborate, so we do also announcements of different events on the platform, and we have also an option where users can interact directly. So going back to the presentation, one of the important components that we are working on within the project is to set up a multi-hazard risk assessment framework, which basically is, helping stakeholders to decide what kind of approach do we need in terms of multi-hazard risk assessment, for which situation, given a lot of different, characteristics, such as the scale at which you work, for what you use it for, want to use it for, how much data availability and the level of expertise, but also what kind of hazards you're looking at and how they're interrelated, and the assets and their vulnerabilities, and also taking into account the dynamics of climate change. So within such a disaster risk assessment framework, we say what kind of approaches would be most suitable in which particular case. That we work this out also in different areas. We have developed one such framework for the Himalayas, where we collaborated with the World Bank in a project in Nepal. And we also did this recently in the framework of this project together with different agencies in the Caribbean, where we worked together with the Caribbean Disaster Management Agency, CEDIMA, and we recently had a workshop also with UNDRR on this topic. So one of the important aspects there is at which scale the risk assessment needs to be done, whether it ranges from a regional scale up to a community level scale. Of course, the aims and objectives of such a risk assessment would be very different from one scale to the next. And also the availability of information would be very different. Here, an example from the Caribbean, which has a number, where the CEDIMA has a number of member states. And so at the regional scale, it's relevant to carry out a multi-hazard risk assessment, for example, for impact-based forecasting. So in terms of hurricane-induced damage. In other cases, you might want to do that at a watershed level approach, where hazards are very linked to particular watersheds, for example, certain hydrometeorological hazards. And of course, in the cross-boundary approaches, many of events might affect more countries or administrative units. As demonstrated here, of course, a hurricane would hit several countries, or in the Himalayan context, events that happen in watersheds that originate, for example, in Tibet, might affect Nepal, and then might affect even India and downstream further. So this scale and objectives are quite important. And the other very important aspect for deciding what kind of approach to use is the selection of, say, why we need it for, what kind of decisions or policy are we want to implement, and for what kind of information is needed for such a decision. And these could be very wide-ranging, from prioritization to land use planning tools to risk financing instruments to multi-hazard early warnings, and that these would all require different inputs in terms of what is relevant for taking those decisions, and also at different scales. So here, a small example of an example of that is for decisions that are taken in the prevention phase. So a scheme that we worked out together with discussions with stakeholders. On the left, we see the main applications that require risk information. And in the middle, we see the different scales at which these decisions have to be taken. And within the matrix, we see what kind of information would be required for that specific combination. For example, at the national scale, for prioritization of administrative units for investments by governments, we would need the relative classes of exposure, vulnerability, and capacity for provinces, districts, or municipalities. And so a higher level of disaggregation than you would need if you do that at a regional level, where, for example, Inform Risk is doing this at the national scale. And so like this, we could define such type of data requirements in terms of multi-hazard risk information for each of the decisions, the actions that need to be taken in the prevention phase, but also in the preparedness phase, as well as in the response phase. So the second important component relates to the interactions of hazards. And I think that is one of the key aspects when we are talking about multi-hazard risk, is to understand how hazards interact with each other. They do that in many different ways. And each of those would also have its implications in the way you would assess the hazard and would assess the risk subsequently. So we look at that in terms of three different types of interrelations that hazards might have with each other, in terms of their type and their causal effects, in terms of their spatial interrelations, whether they are interacting spatially or not, and temporally. There have been quite a number of attempts to try to combine those, but we try to combine those different frameworks into a single one, where we look at multi-hazards in terms of their causal relationships and identify four major types of causal relationship. We look at the spatial relationship of hazards, where we also define four major types, and we look at the temporal relationships, which also would have four. So we can combine those different aspects, and you would have then hazardous events in multi-hazards that have these specific combinations of factors. This would allow us to look at multi-hazard, multi-risk scenarios, and when we also take into account dynamic exposure, so how exposure changes over time, how vulnerability changes over time, and then also the direct and indirect impacts, we will be able to look at how certain systems will be able to function when they are impacted by multi-hazard events, for example, transportation system, communication system, and to assess their level of systemic risk. So by looking at their the redundancy effects within a particular area. And we also will take into account recovery within this concept, because the recovery from one event before being impacted by a next event is also of large relevance. So let's look at some of these classifications. So when we are dealing with independent, with the causal hazard interrelationships, we can think about independent events that have no direct causal relationships with each other. So they could be analyzed separately. Triggering events, they share the same trigger. So for example, a tropical storm might trigger strong wind, but also extreme rainfall that causes flooding or landslides. So the frequency of those events is then linked to the frequency of the trigger. We could have cascading events, so that would be a sequence of events where the occurrence of the next event depends on very specific conditions of the previous event. These are very difficult generally to assess quantitatively, spatially as well. And we have a fourth one, which we call the conditioning events. That means a particular hazardous event changes the terrain conditions or the landscape conditions in such a way that it is more likely that another event might take place, but it's not necessarily triggering that. And so you could think about, for example, a wildfire that changes the conditions of the soil and the landscape, so that it's more likely that rainfall causes floods or landslides. We have also spatial hazard interrelationships, so they might be overlapping. We take a specific class, which we call source and spread, where one hazard actually is the source, but the other hazard is the spread. For example, a volcano eruption may cause ashfall, which spreads out over a large area, but it's related to the source area as such. Cross-border might be a specific case of that, where a particular hazard has effect on different areas at the same time or non-overlapping. And finally, also the temporal hazard relationships, where we look at these resilience curves, as you see it on the right side. A resilience curve plots time versus the functioning of the system, where you could have events that happen after a long time where recovery has already taken place, or consecutive. That means it happens while the area still is under recovery of a previous event. That means impacts would be more severe than if you would have the event after a long time. They could happen simultaneously. And also the onset speed here is important. So whether hazardous events with a slow onset speed are overprinted on ones with fast onset speed. So we've been developing this kind of framework where we have this decision rules developed, where we first look whether hazard combination falls under one of those different causal interactions. Then we would look at how the spatial interactions would be, and eventually also how the temporal interactions would be. So with a kind of a decision rule, and you end up with the possible number of end members of combinations of causal, spatial, and temporal interactions that have implications also to the hazard and risk assessment for those specific cases. So what we developed is then examples of these interactions, where the first three columns indicate different combinations of the type, the spatial and the temporal aspects, a description of the case and an example of that specific event, where we used forensic analysis extensively in evaluating what these historical events had been, and we provide them also references to those. So let me give a few examples of those events. One of them is, the first one is an event that happened quite some time ago, but in my career, it made a lot of impression. I was supervising a PhD student from the Philippine Organization of Volcanology and Seismology, VVOX, who is now the director of VVOX. And we did a study during several years of the multi-hazard events associated with the volcanic eruption of Mount Pinatubo in 1991, where a massive volcanic eruption caused huge amount of ashfall in the surrounding regions, badly affecting the built-up areas, the airports as well, as you see here. But one of the major effects of the volcanic eruption was the generation of pyroclastic flow deposits, which filled the valleys surrounding the crater to a large depth, several hundreds of meters in some cases, with very hot volcanic ash, which caused secondary explosions. But also when we had the rainy season caused extreme erosion within those areas and resulting in very large volcanic debris flows radiating out from the volcano in all different directions, which also changed kind of their paths from one year to the next because of river capture by another river. Here, example of the rapidity of such events. So one before the rainy season and after the rainy season, the same buildings with a very large deposition volume. And say the effect of such a major catastrophic event were, say, more than a decade, where it also resulted in flooding in the lower reaches of such an area. So this is typically an example of such a complicated multi-hazard event that encompasses different processes, causing also different effects over a longer period of time. And where it's very important to understand what happened in such events in order to be able to say something about events that might be similar to that. Another example of that multi-hazard impact is from another of the landmark events where I've been working on in my career, was from 2008, the Wenchuan earthquake in Sichuan, China, where I collaborated with the State Key Laboratory on Geohazard Prevention, now headed by my PhD alumni, Xuan Mei Fan, who's now director of that center. An area of 300 kilometers by 70 kilometers with a very large number of co-seismic landslides, also many of them blocking rivers. And here, one of the most badly affected urban centers called Beichuan, before the event, just after the event, say, where we have as a multi-hazard very large co-seismic landslides and rockfalls that hit directly the urban area, and also upstream caused massive landslide dams, which were eventually broken by the army, but still causing a massive flood throughout the city after about 30 days after the event. And so an earthquake resulting in landslides, resulting in floods, and in the next rainy season also causing massive debris flows because of all the loose sediments. Even after years after the event, debris flow activity was still much higher in this area than before. So this was also a study on how long does it take for the landscape to recover from such an event. So it's not only recovery by say for the built-up area, which was enormously fast after the Wenchuan earthquake, within 3 years rebuilding in other areas than this, but say also the landscape itself, which took a lot more time. Another example I want to mention is much more in time, the impact of events in time, like the event that was occurring in 2022 in Pakistan, where we first had major drought event and say a very rapid onset of the monsoon, causing extreme rainfall in a particular part of Pakistan, causing massive flooding. Currently, we are also studying this event together with a master and a PhD student from Pakistan to look at these compounding events. And the last example from Himalayas about glacial lake outburst floods, which with climate change are showing a very important increasing trend, where we work together with the State Key Laboratory in China to map out the glacial lakes within the Tibetan plateau, and also made estimations as to how these glacial lakes would evolve over time, and develop a statistical model with AI to see what would be the likelihood of breaking, and how would this change with respect to climate variables like temperature and precipitation in different climate scenarios. This then used in combination with runout assessment, so breakout flood modeling for many of those lakes, to see what would be the areas affected by glacial lake outburst flooding. Here on the right, also some examples of these type of glacial lake outburst floods modeling for many different lakes. So these are all examples where Multi-hazards require quite a lot of different modeling approaches, where preferably we would like to use kind of physically based modeling approaches that we could simulate the processes that would actually happen. But in many cases, the parameterization of such physically based modeling approaches are difficult. The other approach is using, let's say, data-driven tools, where artificial intelligence becomes very important. But for those, we would need sufficient historical events, and say the extrapolation of historical events to future climate and the future climate scenarios is often also a very complicated aspect. Here you see a few examples of the type of models that were carried out. Also in an example for the lake outburst flooding that was done in a particular area. The thing with most of these models is that they work well in reconstructing past events, but for future events, there are so many uncertainties that you would have to use it in large, numbers using Monte Carlo simulations, or otherwise actually train an AI model to predict that using physically based models. One of the approaches that we've been working on as well is the use of relatively fast models, and models that are open, also freely available on the internet. Here, an example of such a tool that we developed is called FastFlood. It's available at fastflood.org, and which is developed by my colleagues, Bastiaan van der Bout, who also formed this spin-off company with that. Basically, you can select from any part of the world data that comes from global data sets and do a first flood simulation basically within a minute. But then you can upload, if you have that, your own data sets, or tweak that for specific rainfall situations. And the other major advantage here is that you can see what would be the effect of mitigation measures. So you can online directly include mitigation measures within this type of assessment. It's been applied in different contexts, also for river floods, for flash floods as well, and lake outburst floods is very suited for this type of approach. In a similar fashion, we've been developing a tool for landslides, which is slightly less developed yet than the one for flooding, but which gives also a first estimate of which areas might become unstable under different rainfall and earthquake scenarios, and also say where the runout would be. We can combine those two models also for debris flow analysis. So these multi-hazard modeling interactions, they have an important implication as to assessing eventually the loss. They would have an influence on the frequency of the hazard, on their intensity, but also the way we would establish vulnerability, physical vulnerability in this case, on how exposure would change, also especially with, say, consecutive events, and eventually how the loss estimation should be done. So this specific relation with respect to multi-hazard interactions is a very important component within our work. Another major consideration in terms of which approaches to select is the data availability. Of course, working in data poor areas allows us to do very different approaches than in data rich. And of course, here the scale of analysis is very relevant. As we have global data sets now for most parts of the world, but when we want to zoom in at a specific level of detail, these would not be suitable enough. And so we would definitely need local data. And then we are dealing with aspects on data sharing. Say many organizations work in silo approach, and say the regular updating of data is also of large importance. So there's also a collaboration we are currently doing with UNDRR and with the Netherlands Red Cross 510 organization to look at the maturity of the data ecosystem within countries for doing this type of work. A very important aspect in selecting the methods as well is to look at, say, the future scenarios. So how things would change in future and how we can incorporate, for example, climate scenarios, but also, say, development scenarios within the risk assessment. Here, example from how it's being done in fast flood, where it's possible to select from different climate scenarios, SSPs, for different return periods and future reference years, what would be the expected amount of rainfall? This is being a calculation being done for the whole world, where these kind of return periods can be selected from CMIP6 projected data, but still at a very coarse resolution. The other important component to consider would be, well, the assets and in which sector we are considering to work, as well as also the vulnerability aspect. So how do we characterize vulnerability? Do we look only at the physical, and how we would incorporate, say, the non-physical, the social and economic, environmental vulnerabilities within the framework? We mostly consider that as a two-step approach, where you first look at the physical vulnerability and look at the impacts before bringing the other aspects of vulnerability into it. And finally, it's also about which methods are we going to use, which tools. And there we also looked at different software tools that would be available for doing multi-hazard risk assessment, and what their capabilities would be for answering which kind of questions. These would range from pure quantitative ones to more, say, indicator-based multi-criteria approaches. We also saw that there are no real one-size-fits-all type of solutions. So there are many tools that are very complex, that require specific software knowledge, working with Python, that would not have a graphical user interface, or that are not really designed to work with risk reduction alternatives or scenarios. And so there is still a lot of things to gain in this field. So when we look at the types of approaches that are available, we can differentiate between, say, qualitative and quantitative approaches. Here, a number of these approaches that we've kind of inventorized for qualitative assessments, where I would say multi-criteria evaluation is the most used approach at more regional scales, whereas at local scales, community-based multi-hazard risk assessment is very important, especially when working with NGOs at local level. And for understanding, say, the complexity of impacts, this impact chain approach is relevant. Impact chains, I mentioned that already. That is typically developed in stakeholder workshops, where past events are analyzed, future scenarios are looked into, and also risk reduction alternatives. We've been developing kind of a serious game or a support tool to help in developing such type of impact chains, which consists of a large number of these different icons and cards, which stakeholders can use to reconstruct these impact chains within their own area. And we've also demonstrated that tool, I think also for a group within IDRiM and also last week in the European Commission. So we have also a set of semi-quantitative methods for multi-hazard risk assessment, which are more, say, trying to get information without fully quantifying the expected losses. For example, those that are more exposure-based or those that are based on a multi-hazard risk matrix approach, often used for land use planning. And more towards the quantitative methods. And the upper one here is a scenario-based quantitative multi-hazard risk assessment, which proved to be very useful in local situations with stakeholders that are not able to work with very extensive number of hazard scenarios, but only a limited number of them, and can then see how these limited number of scenarios would result in expected losses. Also, impact-based forecasting is an important tool for multi-hazard risk assessment. It's a direct tool that would estimate the impact in real time based on data from past events. Here we collaborate, as I mentioned earlier, with the 510 organization from the Netherlands Red Cross, which have developed these type of impact-based forecasting dashboards that are based first on the assessment of early action protocols. So for what kind of information should this be done? Then also on trigger models. So depending on the hazard, a different trigger model would be assessed. And the link also with the impact model. So how much impact a particular trigger might cause. And there, again, varying types of approaches could be followed. Now, the last block of methods for multi-hazard risk assessment that we considered would be the pure quantitative ones, where we do probabilistic multi-hazard risk assessment. If we have all that, enough information for that, for example, for earthquakes or for tropical storms, or say events for which you can generate large data sets. AI approaches are much more used nowadays in situations where we have long-term records also of impacts, and specifically for cascading events, event trees in the Bayesian networks are very important. So we provided a recommendation on what type of approach would be most suitable for which particular decision at which particular scale. And our frameworks are actually looking into those, giving advice on which method would be most appropriate in which situation. Now, to end my talk, I'd like to show you a little bit about a software tool that we've been developing also over the past years, in view of the fact that, say, local authorities actually often lack a good tool to do a proper risk assessment as a basis for their risk-informed planning. And the tool should not be overly complex and not requiring the knowledge of, say, working with Python or other software, say, programming tools. It has its own graphical user interface, and it allows, say, people that have a kind of basic knowledge of GIS to do multi-hazard, to import multi-hazard information, multiple assets, so in different styles. It has a vulnerability database, and multi-users can work on a project to look at what would be the current level of risk, how would the risk change in future, and what would be the risk if we would implement certain mitigation measures. So a comparison component. Say the tool works a bit like that. So this is the workflow. We have hazard maps where we look at different types of hazards and their return periods. Different elements at risk or assets are considered, an inbuilt vulnerability database and the administrative unit information. And within the system itself, there's exposures analysis, the loss analysis for individual loss scenarios, which are then integrated into a risk analysis. And then it goes to the spatial decision making, where we have a cost benefit, cost effective, and multi-criteria evaluation part. So typically a system looks like this, where you import your hazard maps, here a flood map, for example, but it could also be a map that has only classes, like a landslide susceptibility map. It is not specific for one type of hazard, so it's generic. You could use it for different types of hazards. Here an example of different types of hazards that are in the same area with its different return periods. It can also handle, say, point line polygons, land parcels, or grids as the asset information. For example, grids could be population density, and lines could be transportation networks, but often building footprints are being used as one of the standard approaches. Here we're also trying to link to existing data. That's actually one of the important follow-up points now, is that we directly link to existing data sources and trying to get the data in before people can upload their own data. Here an example from Open Building Map, which is an attempt to use AI for building footprints to get an estimate of what is their occupancy type. It's very often the biggest problem is that we do not have the attributes required to link them to vulnerability curves. Vulnerability curves are a very important component of a loss estimation, and it would be great if these could be shared among different users. For some of hazards, this has been done, like earthquakes in the Open Quake model. But for other hazards, this is much more complicated to find. And so what we in the tool also have is the option to share vulnerability curves with others. So you can select the most appropriate curve for your specific application. And then do an exposure and loss analysis for your specific study area. So we use that tool for risk and decision making in different situations. First is the current situation. We could look at the evaluation of the current level of risk, but you can also think about doing a risk assessment after a major disaster event, and kind of that has changed the whole situation, and say what would be the level of risk there and how you use it for recovery plan. Then we use the tool in the second level. We use it for planning risk reduction options. So we would see how would the risk components change if we would implement an engineering solution or ecological solution or whatever option is defined by the user. And it would then recalculate what would be the risk, and it would be able to assess what is the change in exposure, but also the change in risk, and say the risk reduction option that. And then we can compare it with implementation costs in a cost benefit analysis or in a cost effective analysis. And finally, we could use it for future scenarios, where we define scenarios in terms of climate change and land use change. And we would see for specific future years how the risk would change and how the implementation of mitigation measures would behave best under different future scenarios. Now, this is an example. These are just types of ways the tools could be used. We also do give training on these type of approaches. One of the types of training is with the UNESCOP APC ICT, which is an organization in Korea, where we have developed an academic module on ICT for disaster risk management. And we also regularly give training courses in Asian countries with UNESCAP, but now also with UN-USA in different Asian and Pacific countries. And we also are currently developing a training curriculum with UNDRR at a national scale to help organizations to train their staff in terms of how to develop the different components of multi-hazard risk assessment for that specific country. We do this like a 3-day face-to-face training for a bigger group, and then we select out of that a smaller group that would get 3 months online individual training, and they would then carry out also a component of the national scale multi-hazard risk assessment, like a single hazard or an asset mapping. So with that, we also offer such type of courses within our university itself. We have redeveloped our courses on the master level, which is 24 months, and we also offer short-term courses as well as distance education courses. So with that, I would like to end my presentation. And I would like to thank you very much for your attention, and I'm looking forward to your questions. Thank you very much.